In this lesson, we're going to learn about evaluating logarithms, and in particular, evaluating them using the calculator. Now, most scientific calculators by default are able to calculate two important types of logarithms. We have the common logarithms, which looks like log x, and that looks a little funny because there's no base listed, but when there's no base listed, it's assumed to be a base 10, which makes it a common logarithm. So all common logarithms are logarithms of base 10. Also, natural logarithms are able to be completed on any of your scientific calculators, and that's where you see ln x, which is a little strange as well, but the ln x is just a shortcut for a log base e. So a logarithm of base e. And e is a little bit strange, I'm sure, if you haven't seen it, but the constant e is an important constant in mathematics, and it shows up in many different applications and has the approximate value of 2.71828, and it actually goes on forever, similar to pi. The decimal goes on forever and it never forms a repeating pattern. The same thing for e. E just kind of shows up in different applications than pi, but you can kind of consider them the same sort of concept. And your calculator probably has the ability to calculate these logarithms, and on the TI-83 I'm going to show you how that works. So let me pull that up and I will begin with an example of calculating log of 5. Okay, so on the TI-83 we have the ability to calculate logarithms. The way we're going to do that is through the log key, log, so that's our common logarithm, and ln, which is the natural logarithm. So those are the two keys that we're going to work with in order to do logarithms. So let me clear that out. Now, in order to do it, it's pretty straightforward. What we need to do, for instance, to find log of 5, we just hit the log button, which brings up log and then parentheses, and then a 5. If we press enter, it gives you an answer, which that answer may look a little bit strange, but it's really not all that strange. So for instance, I'm going to round it to 4 decimal places, so it's 0.6990 to 4 decimal places. So let me write that over here. So log of 5, we're told, is approximately 0.6990. Okay, and with that, the thing that I'm going to do is show you what that means, as it looks like a random number, but it follows the same properties of logarithms. So for instance, if I know my common logarithm is base 10. So the base of my, if I change this to exponential, that is, the base is 10, the exponent is 0.6990. That should result in something that is approximately 5. So if I come over here to the calculator and I do 10 raised to the 0.6990, I get something that's approximately 5. So here's that relationship. The logarithm, the answer to the logarithm, is the exponent to which the base must be raised in order to get the argument. That's exactly what's happening here still. So let's see, a couple of others. Let's say, for instance, we want to do like a natural log of 5. So if I wanted to do a natural log of 5, then I would come over to the calculator and use the ln key. That's going to be a log base e. So plug in the 5 into parentheses, press enter, and I get approximately 1.609. Which, again, it may look a little bit random. Well, I did 4 decimals over here. I'll do 4 decimals over here. So it may look like a very random number, but it is the number to which the base must be raised in order to get 5. So if I did e, which is the base of the common logarithm, to 1.6094, that should be approximately 5. Well, we know e is approximately 2.718 1.28, if I raise that to the 1.6094, then that should be approximately 5. So let's check it out on the calculator. So 2.71828 raised to the 1.6094, and I've got something that's very close to 5. So it works out that way. Now, when it comes to doing e, the calculator knows what e is. So for instance, if you'll notice right above the natural log in yellow or whatever, the same key color as your second button, it is there's an e to the x there, which basically means if you hit second and ln, it takes the value e, which it knows to be the 2.71828 and so forth, and you can just input the 1.6094, and there you have it there. Their answer is slightly different past 4 decimal places, 5 decimal places, just because we rounded e, and it's taking e to as many decimal places as the calculator can hold. But it can do that. If you also will notice above the common logarithm key, there's a 10 to the x. So if you hit second and common logarithm, you get 10 raised to the, so 10 raised to the 0.6990 is approximately 5. So there's kind of shortcut keys for that sort of thing, because you might find that you have to do that sort of thing fairly often. Now, one thing that I find students trying to do with the calculator, at least at first, is trying to do different bases. And so for instance, they try and type in things like, to get a log base 2 of 6, for instance. Putting 2 comma 6 in, something like that. If you try these sorts of things, you're just going to end up with error messages. The calculator will not do anything other than log base 10 and log base e, which you may think of as a something that is, why can't it do any other bases? Something as a limitation, for instance. But it's not really a limitation, because what we have, and I'll show you in the next slide here, is what's called the change of base theorem. And the change of base theorem, so since your calculator can only do common and natural logarithms, and it doesn't have the ability to evaluate logarithms of any other base, at least not the TI-83. Some calculators do, but most calculators don't. The change of base theorem comes in and takes care of that situation for you. So what it says is, for any positive values x, a, and b, where a is not equal to 1 and b is not equal to 1, the log base a of x is equal to the log base b of x divided by the log base b of a. And that may not seem like such a profound statement, but what it means is that you can take a logarithm of any base and change it into a logarithm of any other base. And for our purposes, since the calculator uses only common and natural logarithms, we'll basically use one of these two forms. So if I have a log base a, so if a is 2, 6, 12, 1/5, whatever that base is, I can calculate it using common logarithms by doing the logarithm of the argument divided by the log of the base. Or if you prefer using natural logarithms, you'll get the same result, changing them to log base e. For me, I tend to prefer using natural logarithms, just because when you do it on screen on your calculator, it takes up less room on screen. But it doesn't really make a difference. You'll get the same answer either way. So let's look at some examples. Suppose we want to evaluate log base 5 of 17. So according to the rule we just established, we can do this by taking the natural log of the argument divided by the natural log of the original base. All right, you can kind of think of this rule as like the base of the logarithm goes in the base of this new fraction. Works for me. Okay, now when I do this, I come over to the calculator, enter natural log 17, and you want to make sure you close parentheses here, because if you forget to close the parentheses, then the divided by the natural log of 5 is going to be evaluated inside of the logarithm in the numerator, and you're just going to get a strange answer. So close parentheses and then divide by the natural log of 5. And we come up with, in this case, about 1.760. Okay, that answer is looking a little bit strange. It's a decimal. It kind of goes on forever here. What does it mean? Well, it means the same thing as every other result of a logarithm. So for instance, 1.76 is the exponent to which 5 must be raised in order to get 17. So if I take my base 5, raise it to the 1.760 power, I should get approximately 17. So let's try it out. So 5 raised to the 1.760, and I've got 16.989, which isn't extremely close to 17, but it's just rounding issues. If I had carried the 1.760 to more decimal places, it would have been much closer to 17. And the other thing about the rule here is it doesn't matter if you're using a natural logarithm or a common logarithm. So for instance, if I had chosen to do the common log of 17 divided by the common log of 5, that would have been perfectly okay. Let's see what happens in the calculator. So the common log of 17 divided by the common log of 5. You get exactly the same result, 1.760, 374428. It agrees exactly. So you do have a choice. You can always either use natural logarithms or common logarithms, and you get the same answer either way. As I mentioned, I tend to prefer using the natural logarithm just because it's fewer spaces on the screen of the calculator to show it. Otherwise, there's really no right or wrong. All right, log base 2 of 8. Now, log base 2 of 8 is actually a logarithm that we know the answer to. We can solve this if you change it into exponential form. 2 to what exponent equals 8 is basically what this is asking. And we know that 2 to the third power is equal to 8. So the answer is 3. But I just want to show you that the result through the calculator is going to be accurate. So let's see what happens. So if I'll do a common log of 8 divided by a common log of 2, and I get 3. And similarly, if I did a natural log of 8 divided by a natural log of 2, I still get the same answer. So as I said, my preference is the natural log. Either way, you get the same answer. The result is 3, as we expect it to be. So even if it's something that you can come up with without the use of the calculator, you can still use the calculator. Lastly here, this one's kind of a strange looking one. It's decimals, but that's okay. Log base 2.25 of 0.84. So the way we would do this is take the natural log of 0.84 divided by the natural log of 2.25. So let's see what happens. So the natural log of 0.84 divided by the natural log of 2.25. And we get kind of a strange answer. It's a negative number. I'll take it to 3 decimal places. Normally, you think of negative numbers being something you can't use with logarithms. You certainly can't evaluate the logarithm of a negative number, so the argument of a logarithm can't be negative, or 0 for that matter. But the result of a logarithm certainly can be, as you can have a negative exponent, and the result of a logarithm is an exponent. All it means is, if you raise 2.25 to the negative 0.215 power, then that's going to give you approximately 0.84, which is perfectly valid. And if you try it out here, 2.25 raised to the, and actually instead of typing in negative 0.215, what I'm going to do here is use a feature inside the calculator. You see, the calculator stores the last answer that was found. And you can always reference that last answer if you hit second and the negative key. So second and negative, if you see right above that negative, it says ANS. So now I'm going to take 2.25 raised to the last answer, and that just prevents me from having to type in all of those decimals. And so it works out as we expect. One other thing I want to mention before we move forward, if you're graphing logarithms of different bases, then you also have to use the change of base formula. So let's say you want to graph y equals log base 3 of x. In order to do that, you have to write it as the natural log, write it this way. So the natural log of the original argument divided by the natural log of the original base. So natural log of x divided by the natural log of 3. And then when you graph, it will do a log base 3. So in case you're ever needing to do that, that's what you do have to do. Because again, there's no other logarithms the calculator can do besides natural logarithms and common logarithms. Okay, applications of logarithms. In this lesson, we're going to do the application of a common logarithm to what's called pH level. And pH is a measure of the acidity or alkalinity of a substance. And there's a way of determining how that relates to water. pH level of 7 is perfect water. And if it's less than 7, it's more of an acidic solution. If the pH is greater than 7, it's more of an alkaline solution. So we don't really need to know all of that. That's more of the science part of it. What we need to know is the formula for pH, which involves a logarithm, which just kind of gives us practice with logarithms. So pH is the negative common logarithm of this H30 positive thing, which is referred to as the hydronium ion concentration, which is measured in moles per liter. But again, all we need to really know is the formula and how to use it. So let's see how that works. So let's find the pH of a solution with the following hydronium ion concentration. So in the first example, the hydronium ion concentration is 1.8 times 10 to the negative 5th power. Our formula states that the pH is the negative common logarithm of the hydronium ion concentration. So I just need to plug in 1.8 times 10 to the negative 5th power into my logarithm. When doing that, it would look like this. So negative, and be careful to choose the negative as opposed to the minus. The calculator sees those as two different things, and if you use a minus when you mean a negative, it will give you an error message. So negative common logarithm, oops, already added parentheses, so 1.8 times 10 raised to the negative 5th power. So 4.74. That is the pH of this solution. Okay, next up, if we have a hydronium ion concentration of 9.2 times 10 to the negative 8th, then the pH should be the negative logarithm. Oops, let me clean that up for you. The negative logarithm of 9.2 times 10 to the negative 8th. You just plug it in. Now the textbook and the homework say that you need to do some manipulations with like the 10 to the negative 8th power and reduce it based off the logarithm. That's really not necessary. You just plug it right into the logarithm and the calculator will do everything that's necessary. So in this case we get 7.04. So this is really close to pure water. The first one was a little bit more on the acetic side. And one more here. So if I have a hydronium ion concentration of 6.62 times 10 to the negative 12th, then the pH level is the negative common logarithm 6.62 times 10 to the negative 12th power. So plug it in and you'll get your answer. .18. And I'm just using 2 decimals because that's usually common for pH level. But in the homework, just follow the instructions given for decimals. Okay, let's reverse this. Now let's say we want to find the hydronium ion concentration of a solution with the following pH levels. So for instance, if I have a pH level of 12.8, then what I need to do is using the formula, I'll come over here. So the pH level is the negative common logarithm of that hydronium ion concentration. And just assume that the H30 positive thing is just an X. It's just one variable we want to solve for. We don't, it looks more complex, but that's really the chemistry part of it than it is the mathematics part. It's just one variable we're solving for. We know that the pH level is 12.8, and that's supposed to equal the negative common log of the hydronium ion concentration. So the thing we're trying to solve for is in the argument of the logarithm. So to get that out of the argument of the logarithm, we need to change this into the exponential equivalent of this statement. Before we can do that, I need to divide both sides by that negative. So negative 12.8 is equal to the common logarithm of the hydronium ion concentration. And so when I change this into exponential form, what it's going to look like is the base of this logarithm is 10, so it's going to be 10 to the negative 12.8th power, and that's equal to the argument of the logarithm, which is the hydronium ion concentration that I'm trying to solve for. So if I get my calculator out and figure out what 10 raised to the negative 12.8 power is, then that's going to tell me what my hydronium ion concentration is. So in this case, the hydronium ion concentration is about 1.58 times 10 to the negative 13th power. And that's all we have to do. I mentioned earlier kind of a shortcut to get something raised to the base 10 easy. If you do second and log, you'll get 10 raised to the, and then all you have to do is just type in your pH level there. And that'll get you to the answer a little bit faster too. No big deal either way. It works either way just fine. Okay, so if I have a pH level of 8.8, one thing that we're going to find here in solving these is basically if I take 10 raised to the negative pH level, that's going to give me my hydronium ion concentration. But you can just go through and solve them each time also. It doesn't make a difference. So set your pH equal to the negative log of the hydronium ion concentration. The base is 10, but we can't change it to an exponential form yet because I have to divide by that negative. Now it's going to be 10 to the negative 8.8 power. And that's going to be equal to my hydronium ion concentration. So 10 raised to the negative 8.8. So that's going to be 1.58 times 10 to the negative 9th power. Okay, and lastly, if I have a pH of 2.53. So a pH of 2.53, I would set that equal to the negative logarithm of the hydronium ion concentration, divide by the negative. Oops, I have my logarithm still here, sorry about that. So log of H30 plus, and the common logarithm is base 10, so it's going to be 10 to the negative 2.53, and that's going to be equal to the hydronium ion concentration. So come over to the calculator, 10 raised to the negative 2.53, and we get 0.00295, which isn't in scientific notation already, which would be nice if it was. So we'll convert it. So it basically would be 2.95 times 10 to the negative 3rd power. And that's going to be the hydronium ion concentration in that case. And the reason I know it's to the negative 3rd power is because to get that decimal from here over to the 2, I have to move it 3 spots. So to get it in front of the 2, that is, I have to move it 3 spots. All right, that concludes this lesson, and that'll get you going in the homework just fine. And let me know if you have questions.